Hey y'all, it's Tim Vasquez and welcome to the second dynamics lesson. There's another one that I did about a week ago, and if you check my channel, look through the video listings, you should be able to find that one and begin with that. So let's take a look at this. What do we see here? We look around us and we're in a desert. Is it dry or is it moist out here? Well, if we talk in terms of physics, this is actually a moist environment because we have water vapor. There's some water vapor in the air. We can't see it, but it's there. Now, if we had what we call dry air, there would be no water vapor at all in the atmosphere. The relative humidity would be 0%. So this is a moist air mass, but it is unsaturated. So the relative humidity is not 100%, it's probably around 20% down here along the road. But up in the cloud, there is saturation up there. So relative humidity up there is 100%, and within that cloud, there's continuous evaporation going on, there's continuous condensation down at the molecular level, so we call that a state of equilibrium. So the saturation within the cloud, that's a state of equilibrium. So you're probably wondering about these photos. This was in Ajo, Arizona. I was there about 15 years ago for Swamp. That was, this is me and Shannon Key, and we launched radiosonde balloons out there twice a day at 4 in the morning and 4 p.m., which was interesting. And we did that for 2 weeks. So that's an example where you're working very intimately with moisture, and it's good to have a very solid background on that. The Weather Service page in El Paso has this very neat calculator, and you can see there's all these measurements you can convert. So we're going to start out working with the most elemental expression of water vapor, and that's vapor pressure. And this is the contribution of water vapor pressure to the atmosphere. And I want to thank Max Dodge on Wikipedia for making this diagram available. This shows the concept of Dalton's Law of partial pressures. So these are all the gases that make up the atmosphere. We have oxygen, we have nitrogen, which is definitely 70%, makes up 70% of the air. We have argon, we have water vapor, and we have carbon dioxide. Now, the contribution of these in meteorology, we consider that to be dry air. And this here is what we call the moisture. The contribution of this is the water vapor pressure. And you can see it's a very small amount, maybe a few percent there. But when you add everything up, this gives you the actual observed atmospheric pressure. And you can measure that in millibars or inches. And if you're not a meteorologist, you can measure it in millimeters and PSI. So let's take a look at things. This is the radar right now. We've got kind of a decaying area of thunderstorms, and I'm going to look at Austin just to the south because that's feeding air into these cells. So we look at conditions on the aviationweather.gov site, and we can see that the temperature is about 26 Celsius and the dew point 22, or 78 over 72. So let's put that in that excellent calculator. Okay, so I've done that, and you can see that this contributes about 26 millibars to the atmospheric pressure, which is about a little over 1,000. So the contribution of the water vapor is about 3%, and all the other gases, nitrogen, argon, carbon dioxide, that contributes about 97%. And oxygen, of course, definitely can't forget oxygen there. However, the atmosphere can hold a maximum of 33 right now. So how do we get 33? How do we go up from 26 to 33? Well, one way is we just raise the dew point and bring up more moisture from the Gulf. If we do that, we have a temperature of 78, a dew point of 78, and a relative humidity of 100%. And you'll notice that the observed vapor pressure, 32.75 millibars, matches the saturated vapor pressure, which is the maximum you can have. Now keep in mind that this saturated vapor pressure, that is a term you're going to see every now and then, that is controlled by the temperature. So watch me change that. I'm going to change it from 78 to 98. So keep an eye on this, and if you like, keep an eye on this. Okay, 1, 2, 3. Aha, so you see the saturated vapor pressure went up to 62 millibars. However, the actual vapor pressure has stayed the same because we have not changed the moisture in the atmosphere. So we've got a relative humidity of about 53%. So if you take this part here and divide it by this, you're going to get 0.53 or 53%. So that's how that works right there. So keep in mind that this saturated vapor pressure, that's E with a subscript of S, and the term for actual vapor pressure is just E. So E divided by ES, that's going to give you relative humidity. Pretty simple. Okay, let's take a look at mixing ratio. And this is something that we do use in meteorology. So this is another way we can express moisture. And I took those values, 78 over 72 in Austin, temperature and dew point. And there's something new here. This is station pressure. Now, when we get atmospheric pressure, usually we get this value here, 29.79. That's the pressure calculated at sea level. Like if you drop the barometer down to sea level at Austin, down like some manhole that's 500 feet deep, that's what it would read, 29.79. So we use the station pressure calculator to change that, and here I've put in the values. Austin is 489 feet. I put in the altimeter setting, which is the National Weather Service reported pressure, and that gives us station pressure, which is about half an inch lower. Now, if Austin was a lot higher, like 10,000 feet, you can see that this station pressure drops quite a bit. So we lose about a third of the atmospheric pressure because we go up to 10,000 feet. So that makes sense. Okay, so the station pressure is 29.27, and I put that in the calculator and press convert, and you see what we get for mixing ratio. This is the actual mixing ratio. This is how much water vapor there is in the atmosphere in Austin. So for every kilogram of dry air, we have 17.25 grams of water vapor. Now the air can hold 21.2, so if we divide that into that, we get a relative humidity of 81%. So this is a value that we call W. So actual mixing ratio is W, saturated mixing ratio, which is also dependent on temperature, is WS. So W divided by WS, that's going to be relative humidity. And you can see that if we raise the temperature up to 98, saturated mixing ratio goes up to 41 grams per kilogram. So same basic concept, and that's just a different way of expressing moisture. Now SPC, they do have a mixing ratio page, and see that on the bottom, they show surface mixing ratio. And if you look at the values, we're looking at the blue lines. It's kind of hard to read here, but this here is 17, and that's 18, and that's right around where Austin is. And that's very close to the value that we got right there, so pretty easy, huh? And when we go down to the Gulf, we get into values of 18, 19, and then the pink is 20. That's very rich moisture there. And just as a hint, that's also very high dew point. So mixing ratio and vapor pressure are tied pretty close to dew point. They're not the same, but they are different ways of expressing moisture. Okay, so we've showed you relative humidity. Pretty simple. That's the amount of moisture relative to the maximum that the atmosphere can support. However, we have to keep in mind that the atmosphere can be supersaturated. The relative humidity can exceed 100%. And that's very common, especially if you don't have enough condensation nuclei. And then we've also showed you dew point, and the symbol for that is TD. And that's the value where if you drop the temperature down to that level, so now we have 72 over 72, that makes the relative humidity 100%. Dew point is a very common way of measuring moisture. We see that all the time on weather maps. And then, of course, the temperature is represented by T. Now, another expression of moisture is dew point depression, and we'll see that sometimes on upper air charts. That's simply the difference between the temperature and the dew point. Normally, that's expressed in either Kelvin or Celsius degrees. So in this case, those are the values right there. So we've got a dew point depression of 4 Celsius degrees. So normally dew point depressions below 5 Celsius degrees, those are going to be associated with cloud material. So 5 or below, that's a good number to keep in mind. And when it's 0, that's going to mean the air is saturated. And the expression for dew point depression is going to be T minus TD. So then we have another expression called wet bulb temperature. And this is what we get when we put a wick on the end of a thermometer and we swing it in the air for like about a minute, and eventually the temperature drops to some value, and that's your wet bulb temperature. And that's going to always be between the dew point and the temperature. So the symbol for that is going to be TW. Okay, so we put that into our calculator, 78 temperature, 72 dew point, and you see our wet bulb temperature is 74. So that's just between temperature and dew point, a little bit closer to the dew point, and this is what we would get if we had a wet wick on the end of a sling psychrometer. It would drop to 74, just like that. So we actually do that when we use a sling psychrometer. We take the temperature and the wet bulb temperature, and we go from that, and then that gives us the dew point. However, electronic measuring systems, they actually directly measure the dew point based on the sensors. Okay, then we get into something called virtual temperature. Some of you may not be too familiar with this, but let's go back to that. Let's go back to our gases here. And you can see that we've got this mix of gases that make up the atmosphere. The contribution of water, when we have a lot of water vapor in the atmosphere, this is actually a very light gas. Because, look, hydrogen and oxygen, if you look that up on the periodic table, hydrogen is one of the lightest gases that exists, and we've got 2 molecules here. So moist air is actually less dense than dry air. So our temperature and dew point in Austin is 78 over 72, and that gives us a virtual temperature of 84 degrees. And what that is if we take a dry air mass, remember that's all of the gases except water vapor, just dry air. This is the temperature it would have to be for the density to be the same as what we have here in Austin. So because of the contribution of this water vapor, the gas is actually pretty light there in Austin. So we would have to heat up a dry parcel to 84 degrees to drop the density down and make it just as dense as what we have in this moist sample. So we do this to make the equations a whole lot simpler, and that way if we want to use temperature in equations, we can disregard moisture by making sure that this is all calculated right from the beginning. So let me show you this real quick. We're going to kind of drop the dew point way down and make this a very dry air mass. Dew point of minus 40. Look at that, our virtual temperature has dropped to 78, almost the same as the temperature. And that's because our parcel is almost completely dry. So the virtual temperature equals the temperature. But throw in that moisture, dew point of 77, and our virtual temperature goes all the way up to 85 degrees. So we have to warm up a dry volume of air to 85 for it to equal that density. So I don't know if we have any expressions of virtual temperature on here. Let me take a look. Well, I looked around and I couldn't find anything like that. So just keep in mind virtual temperature, that's a way of correcting the temperature based on the moisture that's in the atmosphere. So we have lots of moisture in the atmosphere here. This is a supercell thunderstorm. So the air is a little bit more buoyant than it would be. It would have less density than if it was perfectly dry. This here is I don't know if you can see it here. This is the Norman tornado of May 10th of 2010. This is it going through my neighborhood where I lived there. And this was along Highway 9 out near Little Axe. And I only took some roof damage, but the neighbor across the street, I don't know, maybe I can show you a picture. Yeah, that's the neighbor across the street right there. That came so close. And what I did is I had bolted out of there. And this is the TV set 8 minutes before the tornado hit the neighborhood. This is across the street from that picture I just showed you. And they're showing, I don't know where the tornado is. Maybe it's off to the right. But as soon as I saw what was going on, I took off down the roads and went south. And I could have bit the big one on that day. And this was the Country Boy store on Highway 9. Unfortunately, took some damage there. Anyway, sorry, got kind of on a depressing note there, but there's a good look at the GO16 imagery right now. Thunderstorms moving through Arkansas and Missouri. And you can see that the stuff around Texas, a little more elevated, not surface-based, and you can kind of see maybe where the surface front might be, something like that right there. So this is the infrared imagery of the Missouri storm, and do you see the great thing about the GO16 data? This is the GOES-R Next Generation. Do you see what's so great? Right here at the top left, see that time right there? Infrared imagery every 5 minutes. And before that, we were lucky to get every 15 minutes. And I think years ago, it used to be every 30 minutes. So this is a great improvement. And we can really use this to track the hot spots to find where the towers are. So if we don't have good radar coverage somewhere, or if the radar network goes out, we can kind of rely on this to kind of see what the cells are doing. Anyway, that's the dynamics part 2. And my notes here on part 3, we're going to get into adiabatic processes, pseudo-adiabatic, and a little bit of the equation of state. So I know these are a little bit dry, but these are the basics, and this will help make you an expert in meteorological dynamics. So hopefully we'll see you next time, and hope you enjoyed it. And please like and subscribe. I would appreciate that. Thanks.